Okay, so let us start the video by recalling these questions. This of course is the field of all rational functions in this n indeterminates, n variables, and S is the subfield consisting of all the symmetric rational functions. We want to know what the degree of this one is over S. So that is one query. Then the next thing is we also want to know the group of automorphisms of this field relative to S. This is the group of those automorphisms of this field under which all the elements of S are kept fixed. Okay, so these are the automorphisms that change nothing of S. It keeps the entire S fixed. And also, can we describe the field of symmetric rational functions in terms of some particularly simple extension of F? So we are now going to answer these questions simultaneously. So what we first note is this. We first note that the symmetric group of degree n, Sn, already fixes the elements of S. In fact, we have used the symmetric group to define S. Since every element of S is constant, well, I should not write constant, but is fixed under any element. Let me write like this itself, any element of Sn, and by that you do of course understand that we are not talking about the literal elements of Sn, that is, we are not talking about any sigma in Sn, but actually we are talking about those functions T sigma that you apply on the elements of this in general, and among these elements those which belong to S are unchanged by any such T sigma. Okay, so that's why any element of Sn is an automorphism of this under which every element of S is fixed, and that is why we have this. Sn is contained in the group of automorphisms of this field relative to S. At this stage, we don't really know whether there is something else in this group besides the elements of Sn. Right now, we only know that Sn is a subgroup of this group. So, by our previous result means one result that we have already seen about the size of this group, and the exact result is Theorem 562. So, by Theorem 562, let us write this first. I mean this thing, this degree. This degree by that theorem is greater than or equal to the order of this group. However, because Sn is a subgroup of this, so this is greater than or equal to the order of Sn, which of course is equal to n factorial. So we have got an inequality involving this numbers. Now we are going to observe something else. Now we are going to consider the polynomial that we have already considered while discussing elementary symmetric functions. Now note that the polynomial, this polynomial t to the power n minus a1, t to the power n minus 1 plus a2, t to the power n minus 2 and so on, plus minus 1 to the power n a n. This is a polynomial whose coefficients are the elementary symmetric functions in the indeterminates x1, x2 up to xn. So this is a polynomial over this extension of f. That means this is a polynomial in this polynomial ring. If we wanted to write in a ring, we would have written this. However, we have written over. So we just write the underlying field. Okay, over this field. So this is a polynomial over this field splits as this. T minus x2 and so on, and finally t minus xn. If you multiply all the terms out, collect the like coefficients and you do everything, then you are going to get these symmetric functions. In fact, you can actually see why that is going to be the case. For example, you are going to get t to the power n from this product, and then for the terms where you have t to the power n minus 1, you get the coefficients which are minus x1, minus x2, minus x3 and so on. So you collect all those terms, you are going to get minus of x1 plus x2 plus x3 up to xn, and that is just a1, minus a1. Like that you will get a2 and so on. Finally, also you see one more thing. I mean, the intermediate terms of course will come according to the pattern in which you will have the product. But ultimately the last term is obtained by multiplying all these xi's. And how many xi's are there? Actually minus xi's. So you have n number of minus xi's. So minus 1 to the power n and the product of all the xi's, which is the last elementary symmetric function, that is an, which is just the product of all the xi's. So that way this polynomial splits completely as a product of linear factors over what? Over this field, our main field. Do you understand what we have written here? This is a polynomial that whose coefficients are coming from this field, and it splits completely over a larger field which is containing this as a subfield, and that larger field is this. Also, the above polynomial cannot split completely over a proper subfield of this which contains this. cannot split as a product of linear factors over any not just any subfield but any proper subfield. But I think I need a bit more ink. Just give me a moment. We have to give the reason for that also. Why such a split is not possible. We have to say that, justify that. So it's not simply subfield but any proper subfield of this which contains this subfield. In other words, we are saying that if you find a proper subfield of this inside which you have this field, then over that proper subfield such a complete factorization into a product of linear factors for this polynomial is not possible. But why? What happens if that is possible? Otherwise, that proper subfield has to contain F. Well, it will of course contain F, because if there is one such proper subfield which contains this, then of course it contains F also, because inside this we have F and all the AIs also. Has to contain F and all the roots of, I think it will be better if we give it some kind of name, no? Or can I just simply say the polynomial? I can say so here, there will be no confusion because this is the only polynomial we are talking about. So let me just simply write above polynomial, roots of the above polynomial. That means if a complete split into linear factors is possible, then such a subfield must of course contain all the roots of this polynomial. But what are the roots? These are the roots, the xi's are the roots. Namely, this. Okay? But then what does that mean? That would mean that since that subfield is containing both F as well as all the xi's, it will then have to contain this extension as well. Okay, because by definition this is the smallest extension of F that contains these indeterminates. Okay, and that is why we cannot have such a subfield, because then it is no longer a proper subfield, it becomes equal to this. How can it be proper? Namely this, and that would contradict the fact that it's a proper subfield. I mean, you could have written one more line also, and that would imply that that subfield contains f of x1 x2 up to xn, and that's why that is not possible. It cannot be possible for a proper subfield, but you understand what this is. So for so its nature of being a proper subfield is being violated. But then what? Then over this extension of this field, our polynomial splits completely as a product of linear factors, and over no proper subfield this thing happens. That is why this is actually the splitting field of our polynomial. So this is the splitting field of our polynomial. Over f of this. And now we recall a result about splitting fields, and that result is that the splitting field of any polynomial of degree n over any field has degree at most n factorial over the base field, and this result was Theorem 532. Since this polynomial has degree n, it follows from that theorem that the degree of this splitting field over this is at most n factorial, less than or equal to n factorial. That this is less than or equal to n factorial. It will be better if I write it down. Okay, this is less than or equal to n factorial. Now let us see what is the relationship among this field, and S. Remember, we already know what these AIs are. Each AI is a symmetric rational function. Actually elementary symmetric rational function, but after all of them belong to S, and already S contains F. So that means this field is itself contained in S. Now, since this field is a subfield of S, that means S is an extension of this, and our field of rational functions is an extension of S, because S is a subfield of that. So let us recall the first result of field extensions regarding degrees of these things. Then you know what I am talking about. I am not going to write the theorem number or whatever it was. You go back to the first section 5.1 and there you get this result, which is just this. The degree of the largest field over the smallest one here is equal to the product of the degrees of the largest field over S and that of S over this. Okay. Now, because this is after all a positive integer, all of these are positive integers, and we now know something about these things, right? One of the things is that the degree of this is greater than or equal to n factorial. Why? Because you see, we have shown just now that the degree of this is greater than or equal to the order of the group of automorphisms of this relative to S, which is greater than or equal to the order of Sn, which is n factorial. So this integer is at least n factorial. But at the same time, this degree, this one, is at most n factorial, and this entire thing is actually a multiple of n factorial. I mean, not n factorial, but it's a multiple of something that is at least n factorial. So what can we conclude from these things? I need to write one more step, then it will become more clear. And that one more step is this. See, this product is greater than or equal to the degree of this, which we already know is greater than or equal to n factorial. So n factorial is greater than or equal to this, which is equal to this, that is greater than or equal to this, that is greater than or equal to n factorial. Let me actually write those things, then it will be even more clear. N factorial is greater than or equal to this degree, and that is equal to times, oh sorry, this is S, and that is greater than or equal to this, which is greater than or equal to n factorial. That means all these things you see now, each one of them has to be equal to n factorial. Hence, this equal to this should be equal to n factorial. We are forced to conclude from this series of inequalities these equalities. Now from these equalities we immediately conclude some things. We thus have mainly two things. First, we see that since this is equal to n and at the same time this product is also equal to n, so this must be equal to 1. We thus have equal to 1 and is equal to n factorial. Now what can we then conclude from this degree being 1? We already know that S is an extension of this, and in fact that's why we are writing degree of this extension. And degree of an extension becomes 1 if and only if the extension is equal to the base field. That is the only case. Hence S is equal to this. In fact, this is something that we claimed when we were discussing those 3 questions. In this way, S has been described in terms of a simple extension of F, in terms of some particularly simple, these are also symmetric rational functions, but elementary symmetric rational functions. So we now have a description of S in terms of those simple things and F. Also, something else has come out. What is that thing? Since let me write like this: n factorial is equal to the degree of our field of rational functions over S, which is greater than or equal to the order of the group of automorphisms of this field relative to S, and that is greater than or equal to the order of Sn, which itself is equal to n factorial. So from these inequalities also we will get equalities. That is equal to n factorial we have, you see, you see, we have already answered 2 of the questions. This is the 3rd question. I mean, this is the answer to the 3rd question, and the answer to the 1st question is this. But besides that, we have also found an answer to the 2nd question from here, because now what we can see is this. But we already have seen that Sn is a subgroup of this and they have the same order, both are finite groups. So that's why they are the same thing, they are equal. So now we know that in this group of automorphisms of this field relative to S, there is nothing else. I mean, only whatever we have in Sn are actually not just the sigmas but those T sigmas. They are the only automorphisms of this field relative to S. Nothing else besides them. And all these things can be summarized, has been summarized in the form of a theorem by the author. So let's just write the statement of the theorem. That will make everything clear. And the theorem is just this. Theorem 563. Let F be a field, and we are going to write some things that we already know, but that's how the author has written. And let this be the field of rational functions in these indeterminates. Then, we need to say what S is also. If S is the subfield of all the symmetric rational functions, then we write the conclusion of the theorem. If S is the subfield or field, anything you can write, it will be understood what we mean. If S is the field of all symmetric rational functions in this, then the following are true. Number 1. Do we have it as number 1, 2, 3, 4 or A, B, C, D? 1, 2, 3, 4. Number 1. The degree of our field of rational functions over the subfield of symmetric rational functions is n factorial. Number 2. The group of automorphisms of our field of rational functions relative to the field of symmetric rational functions is the symmetric group of degree n, Sn. Number 3. S is actually this. And there is a number 4 also. In the course of proving these things, answering those 3 questions, we have found something else, that our field of rational functions is the splitting field of that polynomial. We did not, however, say what these things are now, because we have been saying everything where these are the elementary symmetric functions But already I am running out of ink again. What is happening? I think I need to put some more. The ink is drying up so quickly. Symmetric functions, symmetric rational functions, that's understood. Elementary symmetric functions in these variables. And number 4, this is the splitting field of the polynomial, and this part I can simply erase. Over this, which is actually just S. So that is the summary of what we have done. Now there are some observations regarding this result. The first observation is this. Do you remember that result where we proved that if we have a polynomial whose degree is a positive integer and then it has a splitting field, and the degree of the splitting field over the base field over which we have the polynomial is at most n factorial. And that time we remarked, while proving that result, after proving that result, we remarked that the bound of n factorial is attained, that for any positive integer n and any field and any field f, we can construct a polynomial of degree n over f, whose splitting field will have degree exactly equal to n factorial over f, whose splitting field has degree n factorial over f, and that polynomial is this. I mean, of course, it's a polynomial with coefficients which themselves are elementary symmetric functions, but after all it's a polynomial over f also. So the splitting field of this polynomial is our field of rational functions, and that field has degree n factorial over f. Well, maybe I am saying it a little, I'm not saying it correctly. No, it's not over f, but it's over this field. Okay, fine. So it's over this field, and the degree, however, that's the main point. The degree is n factorial. So that upper bound of n factorial is actually attained. That's the point here. So you should not consider that this f is this f. Okay, that's not the thing. And we have also got another thing, that this thing. We can describe this equality by saying that every symmetric rational function, that means every element in S, is a rational function in the elementary symmetric rational functions, because f of this is equal to S, and this is a classical result, and this result has a name also. It is the result on symmetric functions, and this result can be sharpened to another result, which says that if the symmetric function that you take from here, symmetric rational function, is a symmetric polynomial actually, because polynomials are also rational functions, then that turns out to be a polynomial in the elementary symmetric functions, which is something we are going to prove in exercise 7. And that thing is known as the theorem on symmetric polynomials, just like this is known as the theorem on symmetric functions, and it's a classical result, but it can be proved like this much more efficiently using field extension theory. And that's just it for tonight. After this we have normal extensions and the things that come after that. So that we will see in the next field theory update. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.